Good afternoon, and welcome to Effective Data Lakes on AWS. This talk is a distillation of the lessons we learned in the field from helping various customers build their data lake on AWS. My name is Radhika Ravirala. I am an EMR solutions architect at AWS, and joining me on stage today is Motaz Anani, who is also a solutions architect with our strategic team. So before we kick off this talk, a quick poll. How many of you are or have currently built a data lake on AWS or considering building a data lake on AWS? Fantastic. This is what I expected to see. So let's get started. So here is a quick preview of what we will be covering today. We'll look some motivation behind why organizations are looking at data lakes, some concepts and principles around designing a data lake, common questions and challenges we get asked when we meet customers in field as they embark on this journey, some design patterns to counter these challenges, and finally, we'll look at some security constructs to secure and govern your data lake in an effective manner. Hopefully, we'll have time for Q&A. If not, both Motaz and I will be available outside the room to take your questions. So let's get started. So as you can imagine, businesses today are generating enormous amount of data to the extent of even petabytes a day. A data lake is a design pattern that has the potential to transform businesses by not only enabling you to capture, manage, store these petabytes of data, but also empower you to build complex data processing as well as advanced analytics to drive some insights into your own businesses. So with that, we look at what we have as a data lake on AWS. As you can see in this picture, at the core of a data lake, we have our Amazon S3 service. Now, we chose S3 as the data lake because it's a versatile data store that was designed for scale, has many security features built in, and is very, very inexpensive. Now, to get the data into S3, there are a number of mechanisms. You can bulk load your data using Snowball or Snowmobile. You can stream your data using streaming services such as Kinesis or Kafka. You can simply do an S3 copy using CLI or SDK over VPN or Direct Connect. If you have OLTP databases, you can migrate them using DMS, Database Migration Service, into S3. And finally, you can also leverage hybrid storage solutions such as Storage Gateway to seamlessly migrate your data into S3. And once you have the data in S3, it is important to catalog and search it. Now, traditionally, customers have been using a combination of DynamoDB and Elasticsearch to accomplish this. However, with the launch of Glue, you can now discover, infer schema, have the tables created automatically for you to start working on your analytics. You can also leverage tools like AppSync and API Gateway to provide access and a UI to your data lake using Cognito for sign up and sign in. And of course, security is pivotal to everything we do, and it is the same for a data lake. So you can manage your data lake using a number of security controls we have on the platform, such as AWS KMS, the Key Management Service, IAM, Identity and Access Management, and of course, CloudWatch and CloudTrail to monitor and log your activities. So all this is being done for one purpose, right? There are a myriad of tools in the analytics space that you can leverage to process and consume your data in a data lake. These include Amazon Athena, EMR, Redshift, as well as Redshift Spectrum, and a plethora of others. So now that we have an overview of what a data lake looks like in AWS, we have come to define some key attributes of what a data lake should have. And so if you think about it, a data lake is where all data is in one place and serves as a single source of truth for all your analytic needs. It has the ability to handle structured, semi-structured, unstructured, or even raw data. It has to be inexpensive, has to support schema on read, also support decoupling of storage and compute so that you have freedom from these two resources. And of course, security is, as I said, is critical to everything we do on AWS. You want your data assets and the resource accessing that data lake to be as secure as possible. So all these are critical elements of that form a data lake, and most of the field engagements that we have stress upon these individual attributes at a greater length. So with that, let's see how customers are building and designing their data lakes today. So in our experience, customers build a data lake in a tiered fashion. So we start with tier 1. Now, tier 1 is simply an S3 bucket or a prefix which serves as a single source of truth for your raw data. You want to preserve this raw data as much as possible, and so this is where you want to apply least amount of transformations. This is also a place where you want to apply lifecycle policies to transition them to a lower tiered storage such as S3 IA or even Glacier when you're done using the data. Once you have the data in tier 3, you take the data, raw data, and build what is called a tier 2. In tier 2, your primary goal is to organize your data into partitions, convert them into query-optimized columnar formats like Parquet or ORC, and you have to do some maintenance on this tier as well. For example, over a period of years, you might accumulate a lot of partitions. And some of the customers I've seen have millions of partitions. It is important that you coalesce these smaller partitions into larger partitions for better performance of your queries using these analytic tools. So in essence, this tier is optimized for analytics. And then we move into tier 3. Tier 3 is where you build domain-level data marts. This is where you are taking the data that has been processed and ready for analytics in tier 2 and optimizing it for individual use cases. For example, you might have a data science team, you might have a financial team or a marketing team. Each of them have different kinds of data they need, and the processed data can be pushed into different folders, different prefixes in tier 3, and is essentially optimized for specialized analytics. Most customers that we have been working with who use data lake on S3 or build data lake on S3 also use a data warehouse like Redshift to complement their data lake. And a Redshift data warehouse is really optimized for faster responses to your structured schemas. It helps serve your dashboards and reports for your BI tools. It has fine-grained access control. And most importantly, it has the ability to support joins between the native tables residing in Redshift with the external tables that you define in S3. And so these elements make it an ideal choice to be a companion to your data lake. And of course, when you're done with using your Redshift cluster, you can lifecycle the data back to S3 data lake to save on costs. So with that, let's get into some common asks and challenges that we encountered in the field. And some of them may resonate with your situations as well. So here are some of the sample questions that we get. Can I do streaming ingest into a data lake? Can a data lake replace our database replicas we maintain for analytics? How do I organize data within this data lake? How do I handle late events coming into older partitions? How to perform updates and deletes to the data inside a data lake? How can I run machine learning training on data in a data lake? How can I augment the data with real-time predictions during ETL or even during ingestion? How do we enforce data protection rules in a data lake? And what are some authentication and authorization mechanisms available for your data assets in S3, right? So these are some of the questions that we get, and this is just a subset of the questions that we get. And let's see how we can address these concerns and questions using some examples from the design patterns that we have seen. So you might have a different use case in your own environment. For the purpose of this presentation, we will consider a log or a clickstream analytics or even processing IoT sensor data as a use case. So let's say you have an application that is streaming data through Kinesis Firehose. And that data is destined for S3 because you have configured Firehose to deliver it to S3. And then from S3, you're serving it, the data is being used by analytic tools like Athena, Presto, and Redshift Spectrum, or even Redshift, copying into Redshift cluster. However, there is a problem. You might end up with too many small files, which is not necessarily optimized for analytics. And this could happen because IoT sensor data is tiny, and maybe you have configured the buffer interval and the Kinesis Firehose to be smaller, like 1 minute or 3 minutes. And so you're not gathering enough data for it to become a reasonably sized file. And so how do we address this problem? So you can follow the same approach of streaming your data through Kinesis Firehose. However, you send the data into tier 1, which is the place where we house the raw data, and use a glue ETL job to perform hourly compactions and convert them to ORC and Parquet and put them into tier 2. And then serve your data from tier 2 for all these analytic and other application needs. What about a use case where you need fast ingestion? In this case, you can still configure Kinesis Firehose to deliver to a Redshift cluster instead of S3 directly. And on a frequent basis, on a periodic basis, you can have a glue job connect to your Redshift cluster, perform the ETL, and put the process data in S3. And you can have Amazon Redshift Spectrum act as a single serving layer for all your queries. What if you want a faster ingestion? In this case, you replace your Kinesis Firehose with Kinesis data streams and process your data in micro batches using Spark streaming running on EMR, push the data into an HBase cluster running on EMR, perform regular ETL jobs using Glue, and push the data into a data lake, and have Presto running on EMR federate your queries and serve as a single serving layer for your queries. What if you want the fastest ingestion? You can still stream the data through Kinesis data streams, but in this case, instead of using Spark streaming, which micro batches, you can leverage Apache Flink, which is a first-class citizen on EMR, to process your data, push the data into a HBase cluster running on EMR, and repeat the same process of performing the ETL and then pushing your process data into S3. And this process is the same for serving. You use Presto on EMR, which does the federated query and acts as a federated query and single serving layer. Now, moving on to the next pressing question, which is about replacing your database replicas with a data lake, right? In this case, we have many customers who want to take their data in their OLTP databases, push them into S3 using a service like database migration service, and then have that act as the data sets for your analytic tools. But there is a problem. Updates and deletes creates newer versions of records. So those who have used database migration might have noticed each row in that is being migrated to S3 has an additional column to indicate whether it's an update or a delete. So this is a problem because you'll have multiple versions of it. And so here, again, you deploy the same technique. You push the DMS data into tier 1. At a periodic frequency, you could have a Glue ETL job do the merge of your versions, put them in tier 2, and serve it to your analytic tools like before. So you can also create views to preserve the database view of records. Now, again, in this case, you might have a problem. And that is Grouping records in views can be expensive operation over time. And this is something that we have seen in the field. So how do we address that? So in this case, you want to go through the same ETL process with your tier 1 and put them in tier 2. And you, in addition to doing that, you also take a daily snapshots to preserve the database view of records. This allows all the analytic tools to get a proper view of the records at a certain time of the day. So we'll switch gears here and move to a different kind of use case. One of the common questions that we get from most data scientists is, how do I run my batch training pipeline with my data in a data lake like S3? Now again, the process is fairly straightforward here. You have your data sitting in, raw data arriving in tier 1 like before, and you use either Spark running on EMR or leverage a glue job to do your data preparation. And this data preparation could include feature extraction or vectorization of your data, and you can put the processed data into tier 2 like before. And you can invoke another glue job to provide the data to a batch training job on SageMaker. And once SageMaker is done building a model, it can push the model artifacts to S3. And another Python job or a glue job can invoke a SageMaker API to do the model deployment using the SageMaker's hosting services. Now, what about predictions on a streaming data? And this is a real-life scenario that we have seen with some of our customers, where they have real events coming in from a web portal, and they want to augment this data with some predictions for coming in from a SageMaker endpoint. So in this case, the data can be streamed through a Kinesis Firehose, which is integrated with a Lambda function. And this Lambda function essentially augments your streaming data with predictions from a SageMaker endpoint, and then delivers it to the S3 data lake. Now, this is a problem because it's not a major problem, but it is a problem because it violates our first principle, which talks about least transformations on the raw data, right? So we want the raw data to be as pristine as possible. And so this poses a problem breaking that rule. And so in order to address that, you can still stream your data through Kinesis Firehose, but instead of integrating with Lambda, you can push it into tier 1 and then invoke a glue job that can make an API call to a SageMaker endpoint, augment your data, put it in tier 2, and serve it to your analytic tools. So all these design patterns kind of give us some foundational principles required to build a data lake, right? And the first principle is called principle of minimal ingestion contract. What this means is that you need to decide as a data engineer or an owner of a data lake, you need to decide on a location for ingestion and select a frequency and ingestion mechanism to meet your SLAs. And the producer of the data is given only the location of that S3 bucket or a prefix where they can deposit their files. And once the data arrives, you want to partition that data. And you want to partition with keys that align with your common query predicates. This partitioning is essential to especially your querying needs, simply because partitioning helps prune unnecessary folders that are not needed for your query, thereby reducing your query performance significantly. Because many of the analytic tools that you use are Hadoop-based, for example, Athena or Presto running on Spark, most of them use the underlying Hadoop infrastructure. You want to keep the file sizes to be around 256 megabytes to 1 GB in general, and preferably in columnar format per partition. This allows you to get the maximum benefit from the clusters that are running your query. Of course, you want to compact your data on a scheduled basis. If your data that is arriving is not to this optimal size, you can perform compactions using glue to bring them to at least 256 megabytes, and then start processing them. So then comes the questions. So how do we partition the columns? So the key to partitioning your columns is to know your query filters and your group by columns. And these should align with your partition columns that you will be creating in S3. And if you're using tools like EMR or Hive running on EMR or Athena, then it is better for you to partition this using Hive-compatible format to get the optimal performance. As mentioned before, you want to aim to have optimal file sizes around 256 megabytes or up to 1 GB. And you want to identify the typical query scan range as well, because partitioning often happens on dates. It is important to know if your queries leverage, and you want to partition around the date range as well. So here is an example of how you may want to think about partitioning. Let's say you have a use case where you want to aggregate a lot of time series data, and you have 100 devices, IoT sensors, sending data on an hourly basis. And so you decided on a partition which has device, year, month, day, hour. And you have a data retention or a query scan range of 5 years, and you have one file per partition with each file size being 10 megabytes. Now, if you do the math, it comes to about 4.3 partitions. Now, this is a lot, and this can pose a problem, especially when you have large volume of data. And so to fix this, you can do this. Instead of partitioning by device, you can partition on year, month, day, remove the hour and device, and you bucket your data by the device. Let's say you define 50 buckets, and so your 100 devices are properly bucketed into these 50 buckets. And with that partitioning scheme, you're effectively reducing the number of partitions to 1,825, which is far less than the 4.3 million that we saw earlier. And this is more manageable and operationally efficient way of working with your partitions, because this keeps growing. Another compelling question that we often get asked is, what about mutable data? Customers often have updates and deletes on existing data, and because S3 is an append-only system, how do we handle that? If you have a lot of updates and merges to perform, we highly recommend that you use a database like Amazon Redshift or HBase running on EMR for the time the data can mutate. And once the data becomes static, you can offload the data to S3. That's an ideal way of handling this scenario. There's another way in which you can append to the Delta files per partition and compact on scheduled basis using either a Spark job or using a glue job. So both these approaches have been used effectively in production by our customers. So here is an example of how to serve immutable data. Let's say you have a record coming from your OLTP database, and that database, you have used DMS to push that, and you can add an additional column that says, or that specifies the version for that record. And as that record changes, you get a newer version of that file. It gets appended. And you invoke a glue job on a periodic basis to keep the most recent version and delete the rest. This way, your data set remains lean, and you still get the benefit of having the latest version in the data lake. There are other data lake optimizations that you can perform. Bucketed data, we saw an example earlier. So for additional performance, you can bucket data in each partition on a high cardinality key. This setting is honored by Presto, Athena, Hive, and improves your query performance significantly. So that's an example of how you could write a data frame by using the bucket by API call. You can also order the data for additional performance You can sort the data in each partitions by the secondary key, and as the example shows, there are APIs to do that very easily and to get your data, requested data faster. There are more advanced techniques like Bloom filters. These Bloom filters are space-sufficient probabilistic data structures that is used to test whether an element is a member of a set, and this also reduces your response time significantly when you are querying against a database sitting in an S3. All right, with that, I turn it over to my colleague to talk about some security and governance patterns we have observed in the field, and we'll take your questions after that.
Thank you, Radhika. Finally, I get to get out of my seat. So, hi, everyone. So let me start that section by mentioning 6 timeless security and governance concerns. They apply not really only to your data lake, but also across your, any IT solution, really. Authentication, making sure people are who they say they are. Authorization, making sure people can only do what they are allowed to. Protection of data through encryption at rest and in transit. The presence of audit trails to ensure that we can trace activity back to unique individuals or principals. Centralized governance to ensure that whichever security measures that you want to implement are applied uniformly and consistently across your enterprise data lake. And finally, the ability to achieve and demonstrate compliance to regulators without major fire drills. AWS provides you with the richest and most diverse portfolio of security, compliance, and governance-focused services and features. So 203 significant services and features focused on that. From services that help you establish, manage, and federate identities, such as AWS Identity and Access Management, and our suite of Cloud Directory services and federation capabilities, to services that help you achieve and demonstrate compliance, such as AWS Artifact, which provides you with detailed AWS compliance reports, AWS CloudTrail, which helps you trace API-level activity in your AWS accounts, and AWS Config, which can give you an accurate picture of the footprint in your AWS accounts and how that footprint changes over time. And finally, to services that help you encrypt your data at rest and in transit, and be able to manage your encryption keys in whichever way you choose. And beyond traditional security controls, we are constantly innovating in order to help our customers secure their data lakes at scale. And it is no surprise that machine learning in specific can be applied very effectively in order to automate some of the critical security tasks for your data lake. And that is why late last year we introduced Amazon Mesa. Amazon Mesa can recognize sensitive information or sensitive data in your data lake, such as personally identifiable information and intellectual property. It uses machine learning models for that. Mesa can also continuously monitors and monitors data access to your data lake, and is able to generate and provide alerts if it detects a risk of unauthorized access or a data leak by mistake. But with that quick overview behind us, let's focus our discussion a little bit about 2 key aspects of data lake security: data storage security and metadata security. And let's start by data storage security. So there are 3 key topics that we should consider when putting together a data lake storage security strategy. First is that it's common for our customers to have multiple teams who want to access a single enterprise data lake. So the question is, how do you implement access control for those teams? We will see that this is largely dependent on how you implement data and resource ownership. And here we differentiate between 2 kinds of data and resource ownership. coarse-grained data and resource ownership, and fine-grained data and resource ownership. The second topic is about how to implement fine-grained access control to Amazon S3. And here we talk also about how to control access to S3 from EMR and Redshift. And we also discuss a new exciting feature about Amazon S3 that helps you completely block public access to any Amazon S3 buckets in your AWS accounts. And finally, I'll briefly give you a quick overview of encryption and the encryption options available to you. So let's start by talking about fine-grained access control or fine-grained data and resource ownership. With this strategy, what happens is that teams share fractions of resources, if you will. So if we take a look at the dashed boundaries that we have in front of us, we see that Team X owns certain databases and schemas in a Redshift cluster, and so does Team Y. And both effectively share the same Redshift cluster. We can have a similar situation with an Amazon EMR cluster where both teams also share the same cluster. Obviously, this approach has advantages, and the biggest advantage is efficiency. Shared resources are better utilized. But at the same time, the trade-off that you are going to make here is that access control would be now relatively more complex to set up and maintain. And the reason for that is that EMR and Redshift both have their native identity management mechanisms. So you will have to build your user and identity structures in both of those clusters. Now we can contrast that to coarse-grained data and resource ownership. And with this strategy, your teams own entire AWS resources, such as Team X here in this example. They own their own Redshift clusters, their own EMR clusters, their own Amazon S3 buckets, and even their own accounts. This simplifies much setting up access controls, and moreover, it lends itself naturally to setting up access controls through AWS organizations. And the reason access control setup is simple here is because the primary mechanism that you use is AWS Identity and Access Management. But you can also federate access to your own identity management infrastructure as well. Moving on, let's discuss access control to S3. So Amazon S3 provides you with 3 different mechanisms to control access to data. It provides you with user policies, which can be attached. These are IAM policies that can be attached to users, groups, or roles. Bucket policies, which can be attached to Amazon S3 buckets. And bucket and object access control lists. So usually customers combine all of these 3 mechanisms in order to achieve very fine-grained and flexible access control. This is especially useful if you decide to lean more towards the fine-grained data and resource ownership strategy. In reality, you're going to end up with a blend of both. You're going to end up with a blend, even if you decide to implement coarse-grained data and resource ownership within a single team, you will need to set up access controls for individual team members, but it becomes much easier than having multiple teams sharing a single resource. Moving on to Amazon EMR and Amazon Redshift, both services, when you set up clusters, they can access Amazon S3 through identity and access management roles, which are called service roles. So you can attach IAM roles to your Amazon Redshift cluster. And when you do that, all of your Amazon Redshift cluster users, they have the same level of access to your Amazon S3 buckets. And this is important to keep in mind when you are defining the permissions for those service roles. Amazon EMR has the same thing, basically. So you can also use a cluster-level role to access Amazon S3, but it also provides you with an additional feature. Amazon EMR file system gives you the ability to establish a mapping between your EMR users and groups to certain AWS identity and access management roles. And based on that mapping, EMR will decide how to access which role it should assume when a certain user tries to access S3. it will decide which identity and access management role to assume in order to access Amazon S3. So this gives you more control and more fine-grained control over the permissions that you provide to Amazon EMR users and groups. Moving on to this new feature. So we would like you to be able to use Amazon S3 for public access because this is a feature that is helpful for some specific use cases, particularly website hosting. But at the same time, we want to give you tools for you to be sure that you would not give accidental public access to your data. And that is why we released Amazon S3 Block Public Access. Sorry. Amazon S3 Public Access allows you to block public access for existing and future Amazon S3 buckets that you create in your account. It provides you settings that you can apply at the account level and at the public level, at the bucket level. So on here, let's go quickly through those settings. So the first setting is block public ACLs. This setting enables you to block new put requests or new additions of public object and bucket ACLs. And this is especially useful if you provide cross-account access to Amazon S3 buckets, because if you do that, the other accounts would own their objects, and they have the ability to make their objects public. So with this, with block public ACLs, any new public ACLs are rejected. The second setting is ignore public ACLs. This is like a kill switch on all public access. So when you enable that setting, what happens is that all public, if there are public object and bucket ACLs, these get ignored, so you only have private access to the objects. The third setting is block public policy. So this is similar to the first setting, but it rejects public Amazon S3 bucket policies rather than ACLs. And restrict public buckets enables you, if you have cross-account access, enables you to restrict any access to a specific Amazon S3 bucket to only authorized users in the owning account. So other accounts with cross-account access no longer are not able to access the data in Amazon S3. And remember, this is your right as an account, as a bucket owner. You can deny access, you can delete objects, but you cannot read the contents of the objects. But let's stop here and define what exactly is public. So when we say public ACL or public policy, what do we mean? A public ACL grants permissions to members of the predefined all users or authenticated users groups. So if an ACL grants permissions to any of those groups, it's a public ACL. So it gets treated accordingly by the settings that we talked through. Public bucket policies, it's a little bit convoluted here. It doesn't grant permissions to only fixed values, but the essence of that is that if you have wildcards, if you have permissions, if you grant permissions to any to principles or condition elements that have wildcards in them, that is considered public by Amazon S3, and therefore it is treated accordingly, according to the settings that you configured. Finally, for Amazon S3, there are multiple options to encrypt your data at rest and in transit. So with Amazon S3, you have the ability to encrypt your data client side if you want to, or server side. It's really up to you, where you want to encrypt your data. Some customers, due to compliance reasons, would have to encrypt the data before it even leaves their data centers, let's say. So they use client-side encryption. Or you can use server-side encryption. But more importantly than where you encrypt your data is how you manage your keys and whether you want to manage them. And here Amazon S3 provides you with multiple options. You can manage your own encryption keys in your own identity, key management infrastructure, KMI, and so manage your master keys, master encryption keys, or you can use AWS Key Management Service, which, by the way, integrates with 52 different AWS services. So it's quite integrated with the AWS ecosystem of services including services that are relevant to data lakes, such as Amazon Athena, AWS Glue, and Redshift Spectrum. So all of those support AWS KMS. And you still have full control of your keys. You can import keys, delete keys, rotate those keys, so you have full control over your keys. Now let's move on to metadata security, which is the other aspect of data lake security. And metadata is really data about your data sets. It includes things such as, it's mainly the schema that you overlay on top of your unstructured data in Amazon S3. If you have CSV files, JSON files. So this includes things such as database definitions and table definitions, including column names, column data types, and so on. And AWS Glue provides you with a fully managed and persistent metadata store that you can use for your data lake. This metadata store is Hive Metastore compatible, so you can use all of the Hadoop ecosystem tools that you're already familiar with, so Spark SQL, Presto, Hive, and so on. Also, Amazon AWS services, such as Athena, Glue, and Redshift Spectrum, integrate with the AWS Glue data catalog. Now, here are some of the key things that we see our customers do when it comes to securing and governing their metadata stores. So the first one is very popular. We often hear our customers say that they want to build a central meta store or a centralized data catalog. And this is, if you think about it, it makes sense because not only does it provide like a single source of truth for your metadata and all of your applications, it also simplifies governance and security for your data catalog. And think about it, if you centralize your data catalog, you're effectively having a shared resource across all of your teams, and therefore you need fine-grained access control. So AWS Glue provides you with these fine-grained access controls. You can control access to individual elements of your data schema, databases, tables, and even more kinds of objects such as connections, user-defined functions, and so on. So AWS Glue supports this kind of fine-grained access control. Finally, the AWS Glue data catalog supports encryption of metadata. And this is also one of the asks that we hear from our customers who have certain compliance requirements where they need to encrypt such metadata. And AWS Glue data catalog supports that. Not only does it support encryption of your metadata in the data catalog, it also supports encryption of data that it reads and writes to Amazon S3, in addition to any CloudWatch logs that are generated by your AWS Glue jobs. So here are two examples just to show you that controlling access for the AWS Glue data catalog uses really the familiar IAM policy language that you already know, so there is nothing new there. This is an example of providing cross-account access, where you have a catalog in account A, and you have a certain user in account B. So here we're combining a resource-based policy. So for the account A, this is a resource-based policy that you attach to your AWS Glue data catalog. And then we provide permissions to the principal, which identifies the user Bob in account B. And we also can specify which resources that Bob has access to. On the other hand side, I mean, for cross-account access, of course, we need permissions on both ends, in account A and account B. So in account B, we use regular user policies to establish those permissions. This is another example where you have, for this specific example, we have a development team, and we need to provide fine-grained access to different elements of a single catalog. So for instance, the example on the left here, we're providing only read access to tables that begin with the prefix prod underscore, so production tables. The dev team only has the ability to read those tables and query those tables, but not modify those tables. On the right-hand side, we have a set of permissions which give the developer team full access to development tables. So again, just a simple example to show you how simple it is to have fine-grained access for AWS Glue. We thought of including this just because it represents a nice summary of the capabilities of the different services, just to get a big picture view of that. And specifically, I want to call out the compliance for all of these services. So all of these services are HIPAA eligible, and we have FedRAMP compliance for EMR. But also, of course, we cannot include all of the compliances for those services here. So, please visit the AWS Compliance website and make sure to check, for your particular compliance regime that you're interested in. And it's worth concluding this section by saying that AWS has the broadest and most comprehensive regulatory compliance program across all cloud providers. So things such as ISO, PCI compliance, GDP compliance also when it comes to HIPAA compliance and public sector compliance. So again, please check out our website for any of those programs if you have certain interest. Now that concludes this part. Thank you.
All right. I want to wrap up the session with a little more information about a service that you might have heard at the keynote yesterday, in Andy's keynote. So data lakes are the most popular architectures that many organizations are building today. And you might have heard about many of the cautions and challenges that we discussed today that customers are facing as they embark on this journey. And so AWS Lake Formation is a service that will help with addressing some of these topics that we discussed today. For example, the Lake Formation is a service that lets you quickly build data lakes. You can move, store, catalog, and clean your data faster. It is very easy to get started. You can add the connection information from your data stores you want to move the data from, or point Lake Formation to the data you already ingested through Kinesis, or you can identify a data from an AWS database, and then Lake Formation will automatically crawl and identify the layout of the data that you have in the data stores. You can then train Lake Formation using machine learning to clean and prepare this data. To start training, you provide examples of what you would like your data to look like after it's been cleaned. For example, you can train Lake Formation to dedupe locations in a commercial insurance database. This is just an example. This training process can be as quick as 15 minutes. And inside Amazon, the same technology is used to dedupe and match records for your database. Once you have this, you can also easily secure access using a centralized dashboard. Now, one of the problems that we have seen today is, as Motaz alluded to earlier, fine-grained access control is a complex setup, especially if you have different analytic tools that you're using. For example, if you're using EMR, you can enforce EMRFS authorization for your data sets in S3, but you also need a tool like Ranger to impose fine-grained access control. With Redshift, you have to do something else, and with Athena, something else. So in order to address all these issues, Lake Formation attempts to centrally define your table and column level data access and enforce it across all the tools. All you need is a user that can authenticate to Lake Formation, and based on that user's authorization level, he or she should be able to access the data assets they are allowed to. And then you can also use the data catalog in Lake Formation to search and find relevant data sets and share them across multiple users and accounts. So these are the primary features that are built into this new service. And here's a pictorial representation of how it looks like on the AWS console. The first step or the stage is creating a data lake, and this can be accomplished either by launching a crawler and crawling the data or importing data. And in stage 2, you define table-level permissions or user-level permissions for your glue catalog. And in stage 3, you can search the data catalog, add any additional metadata that you want for your data sets. And finally, you can also monitor and audit your data assets using a central unified location. So so stay tuned for more updates on data lake formation through our blogs and website. And certainly provide us your feedback on how the session was. And we are happy to take some questions if you have any. Yes, go ahead. Yes.
So, did you, what about using DynamoDB for this thing? Is this a valid choice? Why did you select Edgebase in this case?
Sure. The question is, how did we choose, or why did we choose HBase in one of the first architectural patterns that I've shown? Why not DynamoDB? So DynamoDB is a great service. It's a key value store, but DynamoDB also has payload size limitation. So you can't have more than 250 KB of payload, and it's essentially for smaller data items. We are dealing with big data here, and for big data and for data on which you want to perform periodic updates, you would want to use a tool like HBase or Redshift. Yes? Sure.
Yeah, thank you.
Let me know where to stop.
It takes time to rewind all of this.
Sorry.
Is this the right one?
Yeah, I think so. So the question is, so if I have this set up and I write files, in almost real time, maybe seconds, minutes, and then I have a compaction job to have like a second tier of data, and maybe I run it hourly, right? In this case, if I want to access data, for example, with Presto, what is the best practice? What is the recommendation to not just get, the tier 2 data? Because I am obviously interested in real time, right? I don't want to wait for an hour to get results back, right? So how do I query sort of both tiers at the same time, assuming the schema is the same?
Yeah, I mean, you can definitely define tables over raw data as well. It's just a matter of crawling through Glue Catalog or defining a DDL in Athena, or even through Presto running on EMR. You could still define, I mean, I've seen customers define raw tables as well as process tables, and which is tier 1 and tier 2. And that is also an essential step. For example, you want to explore data in terms of what it has. For machine learning or what you want to extract, essentially, you can still create tables on tier 1 and query like you do.
Just to add to what Radhika said, you don't even need to crawl the data if it's all about new files. You just define the schema once, then you can query the data as it comes into S3. So
yes. So my use case is more about what if the data format is the same? Let's say it's already processed. So I really just want to compact it, and I don't want to submit 2 queries all the time.
Absolutely.
So is it something like a view that I should use, or some way to join it somewhere?
Not necessary. If you're already getting processed data, then essentially you're eliminating tier 1. I mean, your tier 1 and tier 2 are the same, right? You can have one table created over your single tier and have queries against that.
Yeah, okay. I will probably have some potentially issues on S3 with consistency when I override files. but that's a separate discussion.
Yeah, so that's the reason. I mean, you want to keep the raw data as is, but if you don't want to do hourly compaction, I mean, you can do every 15 minutes, every 5 minutes as well. It's not necessary. That was for a general batch scenario that I described, but you could do it on a periodic basis using Spark streaming as well, and have it produce your process data at a more faster pace. We have seen faster ingestion, right? You can do faster processing as well using Flink on EMR and have that data available for querying.
So a quick question concerning Firehose.
Yes.
Right now, when Firehose streams in
Yes.
S3, it partitions by
Yes.
I think they. You know what I'm talking about?
Yes,
Is there
absolutely.
something in the pipeline to allow us to specify how we want the partitions to be?
Stay tuned for that. Stay tuned. That's a very common request because it's not in Hive compatible format. You want it in
Exactly.
Hive.
Yeah.
And that's a request that we got from many, many customers, and it's been actively worked on.
Okay,
So stay tuned for updates.
Yeah, because right now we have to run a job to.
Right. For now, you have to run a job, a glue job that can simply, or even a Python script that can simply
Exactly.
take it and change
create
the folder
partitions
or
that
the
Hive
prefix
can read.
name. Yeah.
Exactly. All right, thank you.
Hi. In one of the I think a slide before this, if you can go back, I just want to ask a question there.
You can just use the clicker. instead of-
Let me know where to stop.
Yeah, I think it was one of the first 1-2 slides where you talked about federating the Presto layer, query layer. Can you talk a little bit about that? I was not sure what you meant by that when you said single serving layer.
Yeah, so for data sitting in when you have data that is arriving in through Kinesis streams processed by Spark streaming, you could query the data using Presto. Like you could push it back to S3 and have it being queried by Athena as well. But in this situation, you could use Presto as well running on EMR. This is just an option.
Yes, so because the reason I'm asking is we have exactly the same setup where we have Presto on EMR.
Right.
But my question is more towards the security aspect, the authorization part, wherein
Yes.
how do you suggest we do the authorization part in this scenario? Do you have any-
Authorization for your
Querying.
query. At a table level, column level, or at a row level? I mean, which one? Are you looking at fine
schema
grained?
table level, yeah. Table level.
Okay, so one of the things I could tell you is because Glue today supports fine-grained access control at the table level, if your EMR cluster has Glue catalog defined, when you're launching the cluster, you can specify Glue as the data catalog. And when you specify that, Hive, Spark, and Presto can leverage Glue catalog. And so a user who is using your Presto interface the authorization that are available to him, the security policies apply to that user when he's accessing the Glue data catalog. It doesn't apply to Hive Metastore. It applies to Glue data catalog.
Because we have Hive Metastore right now.
Okay, so for Hive, unfortunately, there is no good solution, I would say, because there is Ranger that can do fine-grained access control, but only for Hive and HBase right now.
But it's not
right?
for Presto though, right? Ranger doesn't work.
They have a Presto plugin coming, but I don't know when it will be available.
Okay, that was my question. Thank you.
So we are happy to take your questions off the stage. We have, we're going to get evicted, basically.
Yeah, we have time. We can take the questions
Yeah, we can
outside.
take the questions here.
Thank you very much for
Yeah,
coming.
thank you.